Okay, so we left off at network address translation. And just to give you a little recap to context switch you back in, we talked about CIDR last class and how it is helpful when it comes to IP address allocation. This allows you to take big chunks of addresses and split them up into smaller pieces. It allows you to take a bunch of smaller pieces and aggregate them into one big piece to reduce the routing table size in a router. So this is just the canonical way we deal with networking addresses as an abstraction. So be very comfortable with this. This is something that you'll need when you navigate the cloud. And one of the nice things about CIDR is it solves this, at least initially, it solved this issue of IP address usage. And so here's a picture from the mid-2000s where you see there's a lot of chunks of address space that are large chunks that have been allocated where there's very few addresses being used. And the reason why is that some of these places don't have that many machines. Right? Like if you are Portland State, initially when we were given our chunk, so one of these was the Portland State chunk, we didn't have 65,000 machines to populate that. We didn't have a single network with 65,000 addresses, but what happened was when we had CIDR and we were allowed to chunk up those blocks into smaller subnets, then I could put a subnet in the dorm, a subnet in computer science, a subnet in class, all of these different things, and then we could actually start to populate our address space to be more highly utilized. But as we ended last class, even with CIDR, the IPv4 address space is still running out. So Aaron gave the last North American IPv4 prefix out in 2015, and the last one worldwide was given out last year. So now we're out. Now we don't have any more IPv4 addresses to give out, and so this motivates something called network address translation. And I should emphasize that this is only one way of dealing with address space depletion on the internet. And the idea here is to make it appear that all connections coming from a local network that's got a bunch of machines is actually coming from a single IP address. So you statistically multiplex all of your usage over a single address and port range. So that's the idea of NAT. And so the examples of this, if you have a cable modem at home, you have more likely than not built-in NAT to allow all of the devices in your home to get that single IP address that your ISP is assigning you on your router. And you're doing this with NAT. On AWS, if you throw in a huge subnet full of machines and you only want a single IP address for all those machines to connect out to the internet with, you're using something called a NAT or an internet gateway in AWS. You're going to instantiate one of those saying, you know, the default router for all the machines in this private subnet will go to this device, and then that's how you will get your internet connectivity in the cloud if you don't want to pay for public IP addresses for every one of those machines in your deployment. In Google Cloud, the equivalent is called Cloud NAT. We're not going to use either of these two things, but you'll just be aware of the terminology from here. Okay, so how does this work? This is a picture of NAT with port translation, which is the common way we do this. So in the upper right, you have your local area network, and as you can see with this network, it's using private addresses. So 10.0.0.0/8, that is a /8 that is not publicly routable at all. Those addresses, you send a packet with that as a destination, nothing happens to it in the global internet. And so you can use any of those addresses to number your private network, which is what is shown here. So there are 3 machines, and then the default router has the 4th interface on that subnet. So in this case, we'll say that maybe we're just going to use a /24, 10.0.0.0/24. And then what we want to do is we want to connect these things to the internet. And the rest of the internet is using regular IP addresses, globally routable IP addresses. So say this is the globally routable IP address that my ISP gives me. 138.76.29.7. And then what the NAT device is going to do, it's going to automatically rewrite packets that come from any of the machines on the right, going out to, for example, Google. It's going to take all of the addresses there and rewrite them to use this IP address. Okay? But you have a problem. If all three machines on the right are hitting google.com, and they're all using the same source address, when packets come back, where's it going to go to? Which one of the three gets them? And so in order for this to work, you have to make sure that not only are you rewriting the source address, you have to rewrite the port number, the source port number in the transport layer. And we'll talk about this in the next slide. You have to do more than just rewrite an address. You actually have to rewrite other headers in the payload. And this is problematic. So we're using this 16-bit transport layer port number, which we'll get to in the second half of this lecture. We have to rewrite that. The NAT device is dynamically rewriting the private source IP address and the source port parameter of your connection. Okay, so to the internet, if you drew a circle around this router and those three machines, to the internet, that looks like one machine. So this is a problem if you're doing stuff like filtering. Like, say someone is behaving very badly. Say this machine is behaving very badly. If you start banning people by this IP address, you'll end up banning the entire network. So if I have a whole organization behind a NAT, and I have an employee who's sending spam, or whose machine gets compromised to send spam, when this IP address-based, sort of firewall rule gets instantiated to ban the whole IP address, it gets everybody. Okay? This is why when you talk about law enforcement, this is why the source IP address isn't enough to prove a case of identity because of this, right? You can't identify someone just on an IP address when stuff like this is going on with the rewriting of network addresses. Okay. So this is the low-level bits of how it operates. So on the right, you have your private network. In the router itself, you're going to have this translation table. And this is just a connection state that says, here's some connection state from the local area network on the right. And this is what I need to rewrite it to on the wide area network on the left. That's what a WAN stands for. So here I have a connection. Source is 10.0.0.1. The destination is this IP address with this port number. And so what the NAT device is going to do, it's going to rewrite the source IP address and port to the globally routable IP address and then some port that's unique going out. And then it will instantiate this mapping in this NAT translation table, right? Because now it needs to know that this on the local area side is going to be equivalent to this on the wide area side. And it has to keep that state. Because when this website responds, it's going to respond and say the destination is this IP address with this port 5001, but in order for this to get routed back to the original machine, I have to go up here and change the IP address and port and then send it back. So that's what's going on. And so this table lookup followed by this rewriting has to happen in order for this all to work. So that is what a NAT device does for you. Are there any questions about this? Yeah.
Are NAT IP addresses, is that 10.0.0.1 also an IP address somewhere else, or is that reserved for NAT?
It could be used for any other, but it's just not routable. So you'll see that we're using, at Portland State, we're using the 10.0.0.0/8. At home, I don't use 10.0, but other people can use 10.0. My neighbor, for sure, I saw his setup, and he's 10.0.0. something. But mine's 192.168. It's from that other private range. On AWS, they use 172.68. They use so those three ranges that I mentioned earlier, the reserved ones, those are up to anybody to use. So you'll have multiple versions of those IP addresses all over the place, but because they're not globally routable, they'll get dropped. As soon as you put that packet on the internet, it'll just get dropped. All routers know that that's a bogus packet and will drop it. Yes?
Does the port on the WAN side get chosen by the NAT
Yes. Yes. There is an algorithm, and it's built into the device itself. So in this case, maybe I'll start with 5,000, and I'll increment by 1 for every new connection. And this will come, I won't cover it in this class, but this comes in handy when you're doing Skype calls, because Skype has a hard time with NAT. Like, Skype is trying to connect into a back-end system where the back-end system doesn't have this mapping to begin with. So we'll talk a little bit about that in a couple slides. Some advantages. Only a single IP address is needed from the ISP to network multiple devices. So this is very convenient for a Comcast or a CenturyLink with a limited supply of IP addresses. You give one address out to your customer, and the customer can network hundreds of devices through the NAT. And so because of the scarcity of addresses, most cloud providers are going to charge you if you use an external IP address. So Google Cloud in particular will have different levels of charging for the virtual machines that you instantiate on Compute Engine. If you instantiate a VM that has no external IP address, that's the cheapest. If you instantiate a VM with an ephemeral IP address, this means that you get a global IP address when that machine is on, but when that machine is off, it gets released and someone else can use it. If you want a static reserved IP address that follows you along and follows your VM along, even if it's off, so you turn the VM on and off, you still have that IP address, this is the most costly. And so be aware of this when you're instantiating resources, that these are the different levels of, because the IP address is a scarce resource, you're going to get charged differently for each one of these. Okay. Another advantage of a NAT is that you have portability. So I can switch my provider from Comcast to CenturyLink, and I don't have to renumber any of my machines on the back end. Likewise, for example, in CAT, we have a bunch of those 10 machines out there. If we switch from this one uplink to another, it doesn't have to be renumbered. I don't have to deal with an IP address allocation that my ISP owns, that if I switch away from that ISP, I have to renumber all my machines, because that's their allocation. So this allows you to switch ISPs relatively easy. Right? There's only a single place where you would have to change. Another big advantage is security. The devices inside of your network, on that private network, they're not explicitly addressable. No one can directly connect up to those machines that are behind that network. It's not visible to the outside world. But there are some issues. So part of being secure is that there's no inbound connection. So this is both good and bad. Like if you're running a bunch of vulnerable servers on your machine, the fact that someone from external isn't able to directly access your server is a benefit, right? Because in order to directly access your server here on the right, there needs to be some kind of connection mapping in that NAT table. But if you haven't explicitly set up that connection mapping, well then all of these connections get dropped. So if you set up a web server here, nobody can get in to connect with it because there is no entry in the NAT device that says, oh, take all web connections, take all connections to this IP address port 80 and send them to that web server. So that's a benefit. But the way Skype works and the way peer-to-peer video calls work, you need someone to be the server, right? Like you need one person to initiate a connection to another person. So how are you going to get behind this NAT router in order to set up a connection between the two endpoints? So that's an issue that these Skype and Google Duo, all of these video calling applications have to do this rendezvous operation because of everyone using these NAT routers. And that's something that I think will get covered in the networking class, but I'm going to skip for this class. If you decide to deploy your own peer-to-peer application, you must take this into account. You must architect your application to take into account the fact that you can't just set up a server and have someone else connect up to it. That's no longer possible. Yeah.
Does that look like port support? Like if I set up a local server for a game, I can connect to it through 10.0.0.1 or whatever. But if I connect to it from like somewhere else, I have to use the actual public IP and then a port. So
Yeah, you have to explicitly, so if you want the incoming connection to this server, then you have to actually go onto the router and say, I want to port forward port 80. Any incoming port 80 on that IP address goes to this local machine on port 80. The other thing that you can do is like, I need to establish a demilitarized zone, a DMZ, and there will be a DMZ host, and that will be this server that gets all incoming connections. So you can set up that thing that way. Most people, like the mom and the pops that are running these things, they won't have the capability to do that. So if you are deploying an application, you have to like completely do it so that it doesn't require configuration on the NAT to get working. And that's a real problem because it used to be you didn't have to do that. You could just build your application, deploy it, and it will work everywhere. Now you have to take into account if you're a gaming application, a peer-to-peer application, a video chat application, you have to take into account that you can't punch through this NAT router very easily. You actually have to come up with some other mechanism. And there are mechanisms that allow you to punch through. It's just that it's really painful is the take home for that. Yes? Having an external server where you have an externally routable server that's serving requests. So like google.com is not peer-to-peer. It's got a server, it's got an external IP address, and everybody knows where to go. But here, you have a private address that nobody knows about, right? Because the NAT knows about it, but only the NAT. But you want to be able to rendezvous. Like this server needs to be able to accept a voice call. And so it could be sending, like you could be sending your buddy, here I am at 10.0.0.1 on port 80, connect up to me. But it doesn't work because this thing in the middle is changing all your IP addresses and ports, and it's not allowing incoming connections. That's where a peer-to-peer application will completely break because somebody has to run the server. And if both of you are behind these NAT routers, how do you get your two connections to each other is the big issue. So the way they do it is I'm going to do a simultaneous connection. I'm going to have two. So if you think about these two things, like this being replicated on the other side, I'm going to probe my router to figure out the sequence number space that it's using and then simultaneously connect so that it magically rendezvous. That's what people have to do. That's what these protocols are doing on the back end, which I wanted to avoid talking about, but because you asked, that's effectively what's going on. The thing is called STUN. It's like network translation traversal or some kind of, it's an IATF standard, but that's basically what you have to do. So this is why it's an issue, right? Like this really changes the way you're deploying applications on the internet to have to deal with a NAT device. Okay, so this leads to the thing that's really damaging with NAT. It's the loss of transparency. So there used to be an implicit assumption that network header that you're sending onto the network isn't going to get changed. Like when you send a network layer packet and like that Russian doll, now you're expecting that people aren't going to disassemble that thing and rewrite all of your stuff and then send it back from source to destination. You're expecting the network to be transparent, right? It's like glass. I send a packet into the network, and like glass, it shows up exactly onto the other side. So now this is no longer the case, because the NAT router is sitting there rewriting not only your layer 3 header, it's actually rewriting the layer 4 header as well. Okay? And so now new applications can no longer assume that their own IP address is valid, right? Like I have a 10. In fact, I know it's invalid if I have a 10.0.0.0. Like I know that's invalid. Like how do I figure out my real IP address? And that's now something you have to build into your application if your application needs to know about IP addresses. Okay? So now you can't assume your IP address is valid, and moreover, you should never carry that IP address or port in your application payloads. It makes no sense to send anybody your IP address and port because that thing's going to be rewritten on the other side. So now this completely broke FTP. So FTP preceded HTTP, is the file transfer protocol, and it was built into this protocol. There's this port command, and as part of the port command, the client sends its IP address and port number, and the FTP server will connect up to it, right? But in this case, with a NAT, you're sending 10.0.0. something and some port number, and the server's like, oh great, I'll connect up to you, but then the 10 packet is basically dropped immediately, right? So it completely breaks this application. The application was assuming the network was transparent, and all of a sudden, because you have deployed NAT, you can no longer do this. So this is, I don't want to whine about it, but this is just what you have to do now when you're deploying an application. This is a fact of life now for networking applications. Okay, so this leads us to IPv6. This is the architecturally blessed way of getting more IP address space. So the idea here is that we should just increase the number of bits in the address. So IPv6 was designed basically for that. But while they were redesigning the network protocol, they were like, you know what, maybe we should redesign all of it. And so they redid the address. They looked at the addressing, the delivery semantics, the quality of service, the security, the routing, fragmentation, and error detection. And they came up with a new protocol. And the short bits of this are, the addresses are 128 bits, so 4 times the address in terms of bits. The protocol itself was simplified. And so they applied the end-to-end principle when it came to IPv4, and they thought that they actually could simplify it even more. I already talked about how IPv4 was a narrow waistline. They were like, it's not narrow enough. And so for IPv6, they got rid of the checksum, and they got rid of the fragmentation headers that were in IPv4. And so this is what you have as a header, just large addresses, and then the next header, which is basically the demultiplexing to the upper layer, a hop limit count, which is a time to live, a version, a priority, and then the length. And then there is a flow label, but that's just a hint. Okay, so this is what an IPv4 address or IPv6 address looks like. You're not going to work with any of these in this class, but if you do, after you get out of this class, come across this, you'll know what it is. IPv6 addresses are specified as 8 2-byte quantities given in hex. And so they're separated by colons. So here there's 1, 2, 3, 4, 5, 6, 7, 8 of these 2-byte quantities. That is a 128-bit IPv6 address. And you can see whenever you have something like this that is hex 10, that implicitly it means that there are 2 leading zeros to that. So this is 2610, 0010, 0020, 0220, etc. That's its IP address. So there's also this double colon notation, and it can be used exactly once. And the double colon means that everything in the middle is all zeros, because you'll get a bunch of all zeros in this network address. So here's an example of catron.cs.pdx.edu, and it turns out this is circa last year when they all had IPv6 addresses. I just checked earlier today, and this is no longer the case. Cat got rid of these IPv6 addresses, but it used to be the case that Catron was this IP address, and you see these double colons here. This means that there are 3 missing zeros in the middle. Okay. So this is the way it used to look. If you you SSH'd into Catron and you did an ifconfig, you get this is the IPv4 address, and you can see it's using the private 10 network on there. And then this is the IPv6 address. And so right here is the IPv6 address. This is, I think, the loopback interface has got that crazy thing. So this is the IPv6 address of Catron. You can also find out the IPv6 address of a particular name. So for example, you could do this for Google. If you do Google dig-t quad A of google.com, you'll get the IPv6 address of Google. And you'll be doing some of these dig commands in the DNS labs later on. You can also try and speak natively IPv6. So here is a special ping6 command where you're going to try and ping a router or an IP address using IPv6 versus IPv4. So there's this whole parallel collection of IPv6 tools that are associated with,
The /128, does that mean that's the whole address?
It's the whole address, yeah. So this is CIDR prefix notation. This is the prefix, and it means all 128 bits must match, and this is my IPv6 address. That is me. The link, this is basically like a subnet. It's a local link scope. That means any address that matches the first 64 bits, so the first half of this, is a link local broadcast. And I'm not going to talk about the scopes in IPv6, but IPv6 gives you different delivery semantics that allow you to do something like a local broadcast. But I'm going to skip that because you probably won't come across it unless you're really deep into the network stack. Okay, so the particle labs have this private IPv4 address space. There are 10 networks, and they're only, so we saw last class that they were only reachable after you connect up into a machine here that knows about the 10 network. So you have to SSH into like linux.cs.pdx.edu, so it's got an external address that you can SSH into, and then from Linux, you can SSH into Catron, because then they both have knowledge of the local 10 network. So that's what's happening. But as it turns out, you can SSH you used to be able to SSH into the particle labs using the particle lab machine's IPv6 address. So it had globally routable IPv6 addresses like this. So you could, if your source network spoke IPv6, you could just do something like this. Say SSH, and I want to use IPv6 instead of IPv4, and this would work. But SSH to Catron would fail because you're saying, I'm going to send to the IPv6 address of Catron, not the IPv4. And the IPv4 address is that 10 network one. So that's just an aside. Okay, so the real reason why I wanted to present IPv6 is to talk about how do we get from IPv4 to IPv6. Like, what is the deployment mechanism for getting everybody up onto IPv6? Eventually, you would want everybody to be able to speak both, right? So that I can go natively between one and the other. But what happens if you're speaking IPv6 and all of a sudden you run into a cloud of IPv4 routers? So what do you do? So the answer to this is to do something called tunneling. You take your IPv6 packet, you get to that IPv4 router, and that IPv4 router is going to take that IPv6 packet and wrap around an IPv4 header onto that IPv6 packet, and it's going to send that IPv4 packet across the IPv4 internet to the other side. And then when it finally gets to the other side, the IPv4 router on the other side will take off the IPv4 header and then send the IPv6 packet along its way. This is called tunneling. So going back to the Russian doll analogy, that IPv4 Russian doll is placed around the IPv6 Russian doll, just keeps on getting embedded, and it basically is treating the entire IPv4 network as a single IPv6 data link. It's treating that thing as a data link layer is effectively what IPv6 is doing to that underlying IPv4 network. And IPv4 is basically a framing protocol for the IPv4 data link layer. And I'll show you a picture of this. But what this is doing is it's building a virtual IPv6 network link on top of a multi-hop IPv4 network. It's basically giving you a virtual network on top of a lower level physical network. So this is why I wanted to introduce this concept. To show you this. So here is an animation of what's going on. You have a packet that wants to be sent from A to F. It starts out in IPv6 land, and on the other side is IPv6, but here you have this cloud of IPv4 routers. And so what you do is you have an IPv6 packet. It goes from source A to destination F. It's got some data. But then when you get to this border between IPv6 and IPv4, you have to encapsulate your IPv6 packet into an IPv4 packet and send this through the IPv4 network over to E. So you see the source is B, the destination is E. And this is the path that this packet will take to the other side. When E receives this packet, it speaks IPv6 all the way off to the right. So then you can just pull this packet out of IPv4 and send it on its way. Okay? Does that make sense for everyone, how this is being done? Because what this looks like is this. Yes?
When the computer gets to B and you send it into the IPv4 network, how does it know where the IPv4 network ends? And how does it know where E is?
So IPv6 knows all of these. Your IPv6 network knows all of these interfaces. So there's a virtual network that is on top of this, and this is the logical view of the IPv6 network. And it knows at this edge, B and E both have IPv4 and IPv6 interfaces. So now IPv6 can say, you know, when you get to B, you're going to have to, your next hop, because based on your IPv6 destination, I know that you need to go to E. So it's doing IPv6 routing, but when it gets to the IPv4 link layer, that's when it has to put the IPv4 addresses of those two interfaces on B and E that have both IPv4 and IPv6. So, yeah. So this is what it looks like. This is a virtual network. This is a tunnel that makes the IPv4 network, physical network, look like a single data link in an IPv6 network. Okay. So it turns IPv4 into a virtual link. And this is what I really want to bring home here, because this is powerful. You're hiding the complexity of an entire IPv4 network using a single IPv6 link. Okay, so this is a segue into network virtualization. And since you're now in either graduate school or the upper division, you have seen many examples of virtualization. Virtualization is a powerful tool to get isolation and a view of I guess, uniformity from a higher level. So this is, you've seen this in CS201 when we talk about virtual memory addresses. Every process on a machine, for every process, the machine makes it appear that they own all of physical memory. So for a 32-bit machine, every process running on that machine thinks that it has all the way from 0 to 4 gigs worth of physical memory. And what the virtual memory subsystem is doing is it's going to map that into the actual real memory addresses underneath. So your virtual view is uniform, but the physical implementation is different and it's hidden from you. But that allows you to, when you start up a process, it allows you to assume that you have everything. You don't have to coordinate address space with any other process that's running on that machine. Yes? For which one? The it's physically happening, but it's implementing something that's sort of a virtual abstraction. Like this is more of a virtual abstraction, but obviously underneath, you're dealing with physical IPv4 addresses, and then you're using basically physical packets to implement something that looks like this in the IPv6. Which one will be on the router? It'll be done on the router, yes. And so there needs to be some control protocol that runs on B and on E to do basically the Russian doll creation and then the unpacking. But yes, this is where you would, I mean, somewhere in the interface between V6 and V4, you need a host that does dual home, that does both and can translate between the one to the other. And that would have so that machine would be running IPv4 control plane stuff to get the IPv4 routing right, and also IPv6 control plane stuff so that it can build the IPv6 virtual network on top of that, yes. And that's a level of detail that I'm not going to go into in this class. I just want you to see how things get virtualized by use of tunneling. Yes?
Is there anything special with having IPv4 going through IPv6 the other way around?
You can do the other way around, yes. You can, yeah. In fact, you can make this, the real point is that you can make your Russian dolls any which way you want. You can put data link layer packets inside of IP packets, inside of data link layer packets. You can do, yes, and we'll talk about this because that's basically where we're headed. And this is programmable packets. So you're programmably creating the Russian dolls of your choice, sending them into the network, and then hopefully they get programmably depacked or unpacked, and then they do hopefully the thing that you want it to do. Yes, we're building up to that, but that's where we're going with this. Okay, we have virtual machines. So you've already done this with your VirtualBox. The idea here is that you have a namespace for your hardware so that you can have two machines use the exact same hardware. So when you're running your Linux, your Ubuntu VM, and you've got a host that's some other operating system, to those operating systems, it looks like they both own the same hardware. But you have virtualized it using a namespace saying, this is for this one OS, this is for another. The hypervisor is figuring out the access and keeping that illusion up for you is what it's trying to do. It's trying to give you that illusion that both of these are multiplexed on the same thing. You can also have virtual network interfaces. So if I wanted to own multiple IP addresses on my subnet, I could just say, you know what, I'm going to set up some virtual interfaces and give them individual IP addresses on this subnet. So here you have multiple IP addresses on top of a single piece of hardware. So if you look at my hardware address, they're all the same, but I have now owned 3 IP addresses. So it's a virtual network interface. And in fact, if you set up your virtual machine in bridging mode, your network interface card has 2 IP addresses. The IP address associated with your virtual machine and the IP address associated with your host. And this is what it's doing for that. It's going to respond to the ARP requests for any of these 3 IP addresses on the network. Okay, but now we care about virtual networks. So one of the most powerful abstractions that you can use is to set up entire networks that are virtual, that are multiplexed on top of something physical. And you could be all sharing the same physical network, but you could have your own virtual topologies on top of it. So that is the magic that the cloud is trying to bring you. So the cloud infrastructure in particular is going to rely on network virtualization heavily. And before I talk about how the cloud does it, I want to talk about the internet, and we've been talking about the internet, but I want to talk about how it first came about. And so the internet was really considered to be the very first virtual network. And so this was in the early 70s when, so packet switching was being used in ARPANET, and some packet switching was being used in radio networks and satellite networks. There were some circuit switch networks, so there was a disparate collection of networks in the early 70s. And the idea is, so here you have ARPANET, here you have a satellite network, Aloha. You might have a packet radio network, you might have a phone network, you have all of these different networks, and you want to be able to interconnect these things, right? You don't want 4 different networks, and you don't want to have to go from one to the other to communicate between the 2 systems. Each one of these systems have different addressing conventions, different packet formats, different ways of doing error recovery, different routing protocols that they implement. And so the idea was, the goal was, how do you get data to go from one network to another? And so this is where Vint Cerf and Bob Kahn's paper, this is the paper that specified the architectural principles behind IP was in this paper. And so the general idea is to create a homogeneous virtual network over this heterogeneous network, these heterogeneous networks underneath. And so architecturally, the idea was to put a special machine, a gateway, that could speak both the ARPANET and the satellite network, just as an example. And then what you would do is implement this portable internetwork layer at both the gateway, so all the gateways would speak this special layer, as well as all the end hosts in these networks. So they're all speaking green. And then when you want to send a packet from this machine to that machine, this machine would send a green payload. This is the internetwork packet. And then what would happen is this machine would know, in order for me to get to this gateway, I would need to encapsulate this payload inside of this blue stuff. So that's what it does. So here is a packet that's embedded into the local format, and it gets sent to this gateway in the local sort of routing infrastructure. And then it gets sent to this gateway. The gateway decapsulates it because it can speak both the blue and the pink. And then this gateway might be attached to a bunch of other gateways as well. It does a routing operation. And it says, where does this packet go to? I have all of these other virtual endpoints all over the internet. And I am going to find out the destination. Say it knows that the destination is in this pink network. What this gateway is going to do is it's going to take this packet and embed it into the local format of the destination. So it's then going to do this. Take that packet, put the pink headers around it, and then send that over to the destination. And finally, the destination will decapsulate it, and you get the green payload back. So what this is doing is it's making these underlying networks a link layer, invisible to IP. So here, you're treating all of this as a single link in the IP layer. So this puts a virtual IP network on top of this lower level physical network. That should look very similar to what we just saw with IPv6 and IPv4. So this is virtualization at the heart of virtualization. Okay, are there any questions about architecturally what's going on here? Okay, so some examples of this. So I like going through a lot of examples because then it makes more sense. One example is with a virtual LAN, a virtual local area network, or a virtual private network, which some of you have used either for work or at school here. So there are many ways to implement this using virtualization. I'm going to show you one way. The application here is that say you have a corporate office on the right, and say you have a branch office on the left, and you have two machines on this network, and you want the network at the branch to appear as if it's actually part of the corporate network. Like you want to fake the branch office and the corporate office into thinking that all of the machines share the exact same LAN. So one way you could do this is to do the following. So say A wants to send L2 frames directly to B. Because they're both on the same IP network, A would ARP for B's hardware address and then get the hardware address of B, and then it would send this Russian doll where I have an IP packet that's going from A to B, and I have an L2 frame that also goes from A to B. And the way this is faked is to have these two VPN routers as part of the network. And what you would do is that you would tunnel this L2 frame in an IPv4 or an IPv6 packet that goes from V1 to V2. And so here is your frame that you want to send to B, and this is a layer 2 frame. And in this VPN connection, I'm going to take that frame in its entirety, I'm going to encrypt it and then encapsulate it in an IP packet that goes from V1 to V2. So again, this is an IP packet from A to B, but in order to get this to the corporate network, I have to encapsulate it in another IP packet that's from V1 to V2, and then I encrypt this thing as part of the VPN connection. So this is allowing me to emulate a LAN over the wide area network, right? So even though they're not physically on the same LAN, virtually they are. That's why this is called a virtual LAN. Okay? So that's just one way of using tunneling and virtualization to implement something that probably everyone has either seen or used before. On the other side, the IPv packet is decrypted, and then the frame can go directly onto the corporate network that goes over to B to finish the illusion. Okay, are there questions about what that thing is doing? Okay. Here is another way of doing a VPN using just IP packets inside of IP packets. So here, and this is something that would be more, you would see this more commonly in the cloud. You would say this is a subnet 10.1.0.0/16. And then on the other side, this is another subnet, 10.2.0.0/16. And you want this to appear as a single virtual router in between those two subnets. And so what you would do is this has got a actual IP address of 20.1.1.1, and on the other side it's 30.1.1.1. You would say, this is your tunnel. You would take this IPv4 packet, and you would give it a payload, an upper protocol, this GRE. This is the Generic Router Encapsulation Protocol, which I talked about way back when in the previous lecture. This is a way of tunneling packets inside of other packets. This is the traditional header that you would use. So this GRE header says, hey, you know what? I have another IP packet as a payload. And so you take the IPv4 packet in the private space, this 10.1.1.1, sending to 10.2.1.1. You would put this Russian doll around it, and you would send it along this tunnel. And then on the other side, this router will just pull this header off and then send the packet directly to the destination. So what this is doing is it's making this entire tunnel and these two routers appear like a single virtual router to your enterprise. Okay? And I show you this. So this treats this public network as a link layer, and this is really the basis for virtual private cloud. So virtual private cloud and hybrid cloud implementation. So when I refer to hybrid cloud, some of these companies, they want to use cloud infrastructure, but they can't move everything to the cloud. Like, for example, OHSU must keep patient data on site. They can't push this to the cloud, but you want your patient data to have access to all of the services that AWS and Google might provide. And so what you would do is you would set up a virtual private cloud to try and onboard your AWS services into... I'm not talking about you, Google. Wrong Google. All right. I don't know how to disable this, unfortunately. I used to not have that problem. Let me put it underneath a bunch of stuff. Okay. And so this is a picture of this. And this is a figure I pulled out of AWS, some of their training resources in AWS. And I think now at this point, you at least know what all of these parts are doing. So here you see public subnet and a private subnet. And the public subnet has these externally routable IP addresses in green because they're public. They also have a private subnet that they belong to. And that private subnet is this /24. So that's how you're specifying all the resources on this public subnet, is to have this as a prefix, and then they each have their external IP address. You also have this private subnet, and it's got a different prefix, and all of these don't have external IP addresses. So that's another part of your network. You might have a VPN gateway. So you want your customer network to logically be on the same network as all of your resources in the cloud. This is what I just showed you is going to implement, right? This VPN gateway, so that you have this public internet that between the customer network and the cloud, but that's treated as a single data link layer, so that you can get this logical view. And then you might have an internet gateway that does so for private subnets, if you want these things to go out into the internet, like say like your home router, you want outgoing web connections, then you would need to specify an internet gateway to give you your NAT translation operation. So all of those things, all of those concepts that we've just covered, and it was a sprint through all of these concepts, those are things that you will end up needing to know. This is a figure from the AWS Solutions Architect material, and this is one of the certifications you can do in AWS. There's the Foundations one, then there's a Solutions Architect, a Systems Operation one, and a Cloud Developing one. This is part of the Solutions Architect one, where you're actually managing IP addresses and firewalls and VPN connections and so forth. Okay. So the next thing I want to talk about are software-defined networks, SDNs. And this is more of a story of how we got here. How did we get to the cloud? And so there was, in the early 2000s, before we had large-scale cloud services, the internet was basically run using distributed routing algorithms that were very unpredictable. They weren't stable, meaning that the routes would continually change under load. And the route convergence was slow. So if somebody had a route update, it would take many milliseconds for the routing to converge because you're doing this distance vector operation that you're broadcasting state and then updating tables incrementally. That makes routing convergence slow on the internet. And on top of that, a lot of the configuration was human intensive. So you're managing routers, switches, firewalls, NAT devices, load balancers with different ways of operating with them. So you might be using an Alteon switch here, a Cisco router there, a Juniper router here. They all have their different ways of interacting with them and configuring with them. And they're all running really complex distributed control software. So it was really hard to manage all of this stuff at scale. You also had this problem of opaque operation. Because all of these things were complex and were basically under proprietary devices, you had a hard time debugging something going wrong in your network. Like if a packet keeps on getting lost, how do you go in there and figure out, well, what exactly caused those packets to get lost? So that's the opacity of operation. It was also inflexible, so you could only support routing based on destination and hop count. So it was a shortest path tree operation, and it's only done by destination prefixes. That's all a router could do, and that's all I have presented you so far. Another issue is that the control plane and the data plane were tightly coupled. So if you have someone attacking you with a huge data-based attack, it would impact the control plane. The control plane would go down with the data plane in the early 2000s. And this would lead to instability under high loads. So in the early 2000s, there was this worm called Code Red. And as soon as Code Red started to hit, you get this high load in the network. And what that ended up doing is it disrupted the control plane, the routing. The routing went completely crazy as a result of the data plane being impacted. And so what you would like to do is decouple the operation of the control plane with the operation of the data plane so that they're not brought down together. In fact, your control plane should really work well. It should work better when your data plane is being attacked than when it's not, because that's when you actually need your control plane the most, is when you're under attack. Okay. The last one, it was all proprietary. So pre-2005, you were at the mercy of a small number of vendors doing high-end hardware. And so Cisco and Juniper were the main two companies that were building all the router devices. And when Google and AWS were going to try and build out their infrastructure and they needed certain features, they were basically held hostage with the Cisco and the Juniper product plan to build out their networks. So that was a big drawback for them. And so this is a pattern in technology. How do you replace manual, opaque, inflexible, proprietary technology? And so you'll see this over and over again in computer science. You go with automatic, programmable. You go with transparent operation, flexible software, open source software, and interoperable technology. So this is the story of IP, like the Internet Protocol. This is also the story of router software. And you'll see this is also going to be the story of cloud providers eventually. Not yet, but eventually this will be there too. Okay, and so this is where software-defined networks were developed, SDNs. It's about 2009. And the idea of SDNs was that there are several things behind SDNs. The first is that you wanted a standard interface to program a network device. Like if you're programming both a Juniper router and a Cisco router, it should be the same. The program that you write should be the same to set up routing on either of these two machines. So you need a layer of interoperable abstraction on your router itself. And that's what SDN provided with OpenFlow. And so this allows you to then enable network device orchestration with uniform mechanisms. So you could have multi-vendor hardware, but as long as they all support the OpenFlow standard of configuration, you would get the same logical sort of functionality. Okay. The other thing that SDNs did was separate the control plane from the data plane. So now you have a central controller in your network to perform all of the scheduling and the routing operations. And then when it comes up with a good forwarding policy for all of the routers in its network, it would just push those out all at once into the network. So the control plane is your traffic policy, and that would be run centrally, and then you would push the decision out to the data plane that just does the forwarding. So now all of the routers in your infrastructure, they're just forwarding devices. They're not actually running a routing protocol anymore. All the routing is done centrally. So this allows a single piece of software to control your network state, your data plane elements. And so this gives you this better transparency. It allows you to debug your network more like you're debugging your programs, is effectively what's going on. Another thing was programmable handling of packets. So you want to be able to push out actions into your network that specify dropping, flooding, forwarding, modifying a header. So for a NAT device, you want to be able to say, hey, you know what, here's a device in my network. I want to push out a NAT function over to that device so that it can now perform as a NAT router in my virtual private cloud. Like my customer says it needs a NAT device, so I'm going to push out this policy that implements a NAT device for this customer on this machine, and then it's going to just come up on their network. Okay, so this came out of active networks in the 90s, but then it really took off in the late 2000s. And the other thing is they want this built on commodity parts. You don't want to have to go out and buy the massive custom hardware that the Juniper and the Ciscos of the world were selling at the time, because they wanted to build this cheaply. Okay, so what are some of the applications of SDNs? One of the things that is implementable with SDNs is to allow you to support predictable routing. So rather than having routing that flaps, that's unstable, you can say, you know what, I want this particular routing policy, implement it, and that it stays that way, right? You don't have a routing algorithm underneath that's dynamically changing the routes without your knowledge. You are actually controlling the routes that are taken. It allows you to implement flexible routing policies. So you can basically base your decision on multiple things, on source IP address, the port numbers you can base your routing decisions on, or even the time of day. So in traffic engineering, one of the things you would like to do is you would like to shift traffic away from heavily used links to ones that aren't used very often during the day. Okay. So that's what this application is. So if you have backup traffic, so one of the things that you'll see in the cloud is the cloud will do daily backups of some of your services. And you want those backups to be taken to places in the network that are completely underutilized, right? You don't want it to be on a heavily utilized link during the day that people are actually using for browsing the web. And SDNs allow you to do that. You can say, you know what, these parts of my network are completely unused during the day. I'll send my traffic over there. Or I'll delay the backup until midnight and then use the unutilized midnight time space to do the backups. So this is the kind of resource allocation that is now being done in the cloud at that level. So you're not, that's your policy, not hop count and not instantaneous load. Another thing you can do with SDNs is break net neutrality. So if you're Comcast and you're like, hey, you know what, I don't really like everyone using BitTorrent. I want BitTorrent traffic to go onto this part of my network, and I want all of my Comcast streaming services to go on the better part of my network. That's what SDNs allow you to do, to segregate traffic and then discriminate, which is whoever. So whatever policy, if that's considered good or bad, that remains to be seen. Another one is DOS evasion. So if someone is launching a denial of service attack at you from a particular region, you can, so for example, if you have your service deployed in multiple places around the globe, and someone from Australia is trying to bomb you, then in your peering point in Australia, you can push out a policy that says, drop all traffic from this particular person. And then this allows the rest of your network to evade the denial of service attack. So you could do a policy like that. This is something that Cloudflare does. So Cloudflare has all of these presences in all of these locations across the world. and then you sign up for their service, and if they see you getting bombed by a particular machine, they can push out a filter all the way up to where that machine is located to drop that traffic preferentially. And that's done based on the source, not just the destination of the packet. So that's another application for traffic engineering. The one we care about is cloud computing. So if you've already used Compute Engine, you can see when you bring up a Compute Engine instance, you have all of these options. Even if you haven't, and when you do your Compute Engine labs, when it says select a machine to run your stuff, you'll see a whole bunch of options. Up here in the top, which is not shown, is the F1 Micro, which is the free tier. You should be choosing that more often than not in this class, but I have the more expensive versions. If you look at these, you have all these things called vCPUs. vCPUs are virtual CPUs. So typically, a CPU has a whole bunch of cores in it. Like the largest core CPU here is 96 core. So there's a machine that's got a whole bunch of, it's a multiprocessor machine, and within each processor, there are multiple cores. And so your machine can have up to 96 vCPUs, but if you do a single vCPU, you could, like if you're sharing a vCPU with 95 other machines that are one vCPU machines, you have 96 virtual machines, and each one of those virtual machines has their own IP address range, might have their own external IP addresses, and so right there you have one machine that needs a whole bunch of virtual networks to be instantiated in order to support the 96 clients that are on the machine. And you would do this programmatically. You would not want some poor network engineer to go there and whenever I click a new virtual machine, for them to go plugging things in and out of a device. You wouldn't have that. You want to just send the program over to the router to configure that. And that's what an SDN allows you to do. So the reason why we have these point and click cloud deployments is because underneath we have software-defined networks doing all the work for us. So that's what's going on when you have these virtual machines that are all sharing the same physical infrastructure. So for that same physical infrastructure, you only have one machine, one network connection to one port on a switch, but you're multiplexing 96 potential virtual networks and virtual machines on top of that one physical piece of hardware. And that's virtualization up and down the stack. It's virtualization in the operating system, in the processor, in the network, in the network interface, and in the network itself. Okay. So you will do this. So it actually extends not only to the machine level, but to actual networks in the cloud. So that picture I showed you earlier of AWS and the virtual private cloud, you could have your customers implement all of those in multiple copies of those on top of the same physical infrastructure. So again, the same idea. And you will do this when you do the next week. I'll talk about content distribution networks. You will, with one click, deploy an entire content distribution network that is a virtual network on top of Google Cloud's physical network. So there'll be a cluster in Europe, a cluster in Australia, one on the East Coast, one on the West Coast. And so you'll be building a virtual topology on top of the physical infrastructure that Google provides to give you this, like basically a Netflix of your own, is the idea. Okay. Okay, so the last thing I want to talk about with SDNs is to take a look back at where we came from. So out on the left, this is when I was graduating, this is what we were dealing with, and this is what I was reasonably good at. And this is more of an IT kind of sort of skill. And if you looked at all the things that have happened in terms of automation and being able to deploy things with software, you're over here now on the right where there's all of this software that is running everything that we do. And so this is the difference. It's sort of a meta lesson when you're looking at what kinds of skills do you want to develop as a professional. Back when I was a student, there were all of these certifications that people were being encouraged to do. So learn how to configure a Cisco router, learn how to configure a Juniper router, learn how to configure a Microsoft operating system. And now all of that is being replaced by programs. And so this is the reason why I recommend people go the programming route, right? Because all of this stuff could be replaced by a program that does the same thing. And in fact, if you, I listened to a podcast. Any of you in the site reliability engineering class here? So there's a podcast by an SRE from Google. He's like, anytime we go manually fix a problem, the next thing that we do is we write a program so that nobody else has to go manually fix the exact same problem. And so this is where you got to be able to write programs, because eventually your skill at configuring a device manually will be replaced by a program. So that's basically the take home for that. So yeah, learn your CS and your programming skills, and then hopefully the IT stuff will eventually be obsoleted. So I'm going to take a break there before I finish the network layer, because that was a lot in one. So I'll give maybe a 5-minute break, and then we'll do the next thing. Okay, the last thing I want to talk about in the network layer is ICMP. So this is the figure from the beginning of the network layer. And off to the right, there's this error reporting and router signaling protocol. And that's what ICMP is. So it stands for the Internet Control Message Protocol, and this is a protocol for passing messages, control messages back and forth between hosts. The two that we're going to look at are the ping, which you've already used probably to basically see if a network IP address is up and operational. The other one that we're going to use is TTL expired, and this is for traceroute, which is part of your lab. So if you recall the IP header, there is this header field called time to live. And what this time to live is a maximum number of hops that this packet should take before the network should discard it. Now the reason why this exists is because they were really fearful of sending a packet in the network, having it get caught into a routing loop, and having it be there forever, right? And then to get a network in a state where all it's doing is routing packets in a circular way. Because routing loops were actually quite common in the 80s and the 90s, temporary routing loops. And so they needed a mechanism to protect against that. And so they would set the time to live to 32. And there weren't 32 hops from every source to destination. It was more like 13 or 14 was the maximum number of hops between any source and any destination on the internet. And so on each hop, a router will take that field and will decrement it by 1. And that's part of what the IP protocol processing is. When a router gets a packet that's got a TTL of 0, it will drop that packet, and it will issue a ICMP TTL expired message back to the source to let the source know that it dropped the packet and where it dropped the packet at. And so this is often being used to discover routes and their delays. If you want to know the route from here to Europe, to a particular university in Europe, you can just use this mechanism to figure out all the individual hops along the way, and I'll show you how. And so this is the program traceroute, and it measures the delay from the source to the destination on an end-to-end path. And so this is how it works. The first thing you do is send a packet with a TTL of 1, and then that gets sent to the first hop. It gets decremented. The packet now has a 0 TTL, and it gets dropped, and the TTL exceeded gets sent back. And that round trip time is recorded. And so now you know the IP address of the router that dropped your packet and the delay. How fast did it take to get to that first router and back? And then you would do it with a TTL of 2 to find the next router. And you keep on going until you reach the destination. And so this allows you to figure out where all of the hops along the way are located and how the latency between you and that router. Okay? So that's what's going on. And then trace route will continue all the way until it reaches the destination. So this is going to be used in your labs, and I wanted you to see it work, because I think in your CDN lab, I'm going to have you do a trace route between wherever your infrastructure has been deployed back to Portland, just to see the distance and the delays associated with wide area internet links. So I'm going to show you a small demo here. We talked last time about our access point, the Northwest Access Exchange down on the Pittock block. Almost everything goes through there. So what I'm going to do is I'm going to have you trace route. You can play along if you'd like. Trace route 1.1.1.1. This is the Cloudflare DNS that is basically, it's claimed to be the fastest DNS resolver because Cloudflare has put 1.1.1.1 everywhere. And we'll see where everywhere means in Portland. We'll see where that goes. Versus Google's. So 8.8.8.8 is Google's DNS resolver. And then we can actually see, well, where is this located? And what is the delay between Google's DNS resolver and Cloudflare's? So here's an example of a trace route to 1.1.1.1. And I don't know if you can see that, but you can see that it's sitting there right on the NWAX. So it's a directly connected, so they probably have something right at the Pittock block, right? And it's 1.5 milliseconds away to contact that resolver because it takes a packet 1.5 milliseconds to hoof it down 10th Avenue. And then you have a trace route of 8.8.8.8. And you see this is 5 milliseconds away. And it goes through the peering point in the Pittock block, but then it has multiple hops. And it turns out this 8.8.8.8 is actually in the Dalles. So this is a little bit slower than what you would get with a peering point that's just in the Pittock block. Now, Google could get that 1.5 milliseconds if it actually put something down where this thing is on NWAX. But at least you can see all the different hops that it takes from your machine to some other destination on the internet. Yeah.
I'm trying to follow along, and I get one address that is followed by a bunch of wildcards.
So not all routers will want to respond. And so what happens is if they just drop the packet and they don't tell you, then you have no way of measuring the round trip, and then you'll get the star. And in fact, if the destination that you're trying to reach drops them at the front door, just deterministically, you'll never terminate. You'll just sit there and get stars. Yeah, all right. So only certain ones. So if you can actually get that packet all the way to the end and then get the response without having the ICMP being dropped deterministically, then you can get a proper measurement. But some destinations will they'll say, I don't want to respond to this at all, because this is considered slow path processing. Like routers want to do the common operation really fast. An ICMP message is slow to generate because it's so rare that a lot of routers would be like, I don't even want to deal with ICMP, I'm just going to drop it. So that's why you'll get the stars. The other thing I wanted to do was do a trace route to someplace in Britain. And the thing with the routers is that they're often named with machine names that reveal the physical location of these routers. So you can see it goes to Seattle. I don't know what the MIS2 is, but Minnesota is there, Cleveland is there, Ashby, I'm not sure, Washington, London, and then to Cambridgeshire. So you can actually figure out the delays, and you see the transatlantic link is right here from 14 to 15. It goes from a 63 let me see. Well, this is sort of a transcontinental, and then this is the transoceanic link, 14 to 15. So this is a way to troubleshoot your paths going through the network. Traceroute is just a useful tool for that. Okay, and so with that, that is it for the network layer. Are there any questions? Okay, so I am going to just start